Hello. This work represents the project that aims at providing a tool to facilitate the day-to-day workings of the city planning authorities. Welcome to Oversight. You are greeted by a login page when you open the application URL. I will log in with admin credentials. On logging in, the default Maps menu is open. At the top, we have tabs for all the services we support. The first tab is the Traffic tab. Clicking on this draws colored lines on the roads, representing the current traffic situation. This data refreshes every 10 minutes. Green lines represent free-flowing traffic, yellow lines represent slow-moving traffic, and red lines represent even slower-moving traffic. This gives the city management authorities and transport service providers a good idea of the traffic congestion levels in the city. When we click on the Pollutions tab, various custom markers are dropped on the map, showing the pollution indices for the surrounding areas. The position of these markers was decided by using machine learning, evaluating how pollution ratings usually vary throughout the city. The icons are colored with the scheme red, yellow, and green, based on the air quality of the area, in improving order. This data is updated every 30 minutes. If you click on any of the markers, a graph presenting the pollution index predictions for the next few hours appears. The lower the index, the better. Moving on to the Bikes tab. Markers for all the Dublin bike stands are dropped on the map. You can hover on the pins to see the name of the stand and the number of bikes and empty slots available there. This data is refreshed every 15 minutes. You can click on the pins to see a graph predicting the number of available bikes at the stand. This can help the authorities better manage their resources depending on the traffic congestion levels and predicted bike availability. The system automatically generates an alert whenever the number of available bikes at a stand reaches a threshold of less than 25% of the total capacity. We will talk more about the Alerts module in a bit. Lewis, Bus, and Dart tabs work in a similar fashion. When you click on the respective tabs, markers for all Lewis stands, bus stops and Dart stations are dropped on the map. You can hover over each marker to view the stand/station name. The system gives the users the ability to click on any bus stop marker and view the buses scheduled on that stop in the next 1 to 2 hours. Similarly, for Dart and Lewis, you can hover the markers for station name and click them to view the timetables for the next train or Lewis services. Please note, all the timetables and schedules are retrieved in real time from the government website. Even though the application relies on government-provided APIs for transport-related data and a third-party API for pollution-related data, it is still fully functional offline. Upon retrieving data from these external agents, it is stored in our application database. Once the application requests this data, it is retrieved from the database and stored in the local browser storage so that it is available even when there is no network connection or there is an issue with any of our servers. Let's have a look. We will switch off the Wi-Fi of this machine and try to use the application. We will now turn the Wi-Fi back on and talk about the next module. In this section, the User Management module and System Alerts module will be discussed. First, we'll discuss user management. For our project, we have two user personas. First is a city manager and the second is a service provider. City managers have access to all the features of the application. The service providers have restricted access to the service they are responsible for. Let us log in to the application as a city manager. Here you can see our city manager can access all the information including traffic, pollution and service providers. City managers can add other managers and service providers via the user management portal available on the application here. Let us create a bike service provider user via the portal. On clicking the button Create User, we receive information that the user is created successfully. Let us try logging in with the new service provider we created. As we created a bike service provider earlier, you can see our new user has only bikes permission and no permission to create new application users. Moving on to the Alerts module, alarms can be generated automatically by the system as well as manually by city managers. First, we'll explain the manually generated alarms. The city manager can generate an alarm for a specific location on the map by clicking at the location. Here you can see the above pop-up represents the system-generated alarm based on the threshold configuration. The alarm shows the description as bike availability low. System-generated alarms are for city managers specifically, and city managers can decide if the alarm needs to be forwarded to the specific service provider. Now coming back to manual alarm generation. Let us generate an alarm manually. Click on the map and enter the message. Select service providers whom you want to send the alert to, set the priority of the alert and click on Submit. Let us see if our bike service provider received the alarm. Here we have the alarm with the message. Users can either click on Take Action or close the alarm. Let us go to the Alarms page. Here we can see the alarms that require attention from the bike service provider. The service provider can click on each alarm and see the related details and take action as required. Moving on to the system-generated alarms. You saw we received a system-generated alarm earlier for low bike availability. Let us forward the alarm to the service provider by clicking on this button. As we can see here, the bike service provider received the alarm and now can act accordingly. This section is an attempt to design and implement a basic server health monitoring system architecture that monitors the state of the server and redirects the traffic to the secondary server in case the primary server goes down. The reason for implementing this is to make our application servers more distributed, in order to provide greater availability, scalability, and reliability. Currently, there are 2 servers in the demo, but the solution is scalable for more than 2 servers as well. This is the overall architecture diagram, of which only the health monitoring aspect will be discussed. Here we have our 2 Django app servers, which can be either separate machines or multiple Docker containers. Basically, these are 2 replica servers hosted anywhere. Both the servers send their status to our MongoDB collection, which is the HM data collection via a cron job currently configured at 1 minute. As soon as the server status reaches the database, our health management server will compute the primary and secondary servers and insert the decision into the server status collection. Our load balancing gateway initially calls the primary. If the primary does not respond, the gateway calls the health management API, which is hosted on the health management server, and returns the result from the server status collection. This result is then used to redirect the request to the secondary server. As you can see here, we have the gateway code directory and the Anaconda terminal. We'll just start the gateway. Once this is done, we'll go to the app servers, which are Django servers, and start them on both the machines. Once the servers are up and running, we'll go to the frontend application page and access the API pointing to the gateway. Once the bikes button is clicked, you will see the request comes to the gateway, which forwards it to the application server right here. Now let's just kill one of our first app servers. Again, if I click the bikes button, the gateway sends the request to primary, and when it doesn't respond, it redirects the request to secondary, which is elected by the health monitoring server shown earlier. And the secondary responds by returning the desired response. We can see that there's no impact on the front-end application when we killed our first application server. Thank you.